In this lecture, we will discuss the continuous time unit impulse function, which is graphically represented as a, an arrow at instant 0, and we say it's delta of t, and this delta of t is known as the unit impulse function. So if you see, it's a function but it has duration 0, so it's a kind of idealization, right? That you have a signal with 0 duration. So we will come to this representation at a later stage. I'll discuss how we get this representation, this graphical representation, and because this delta of t, it's a very important function. It's just like the building blocks of all the signals. You would see all the signals that are made up of this delta function, the unit impulse function. In this we will also discuss the sampling property, the sampling or the shifting property of the unit impulse function, the sampling or the shifting property of unit impulse function. And I would like to show you the some mathematical expression in which we would use delta of t in multiplication of a signal, and we would see what is the result of the signals which are usually some function x of t, and when you multiply it with delta of t or some other versions of this delta of t. Let me write it properly. This is actually delta of t. So we would see that what is the result of this kind of thing, because later on you may be using it in integrals, right? So you may be using it in integrals, you may have expressions something like this. So how to solve those type of integrals, we will see this in the lecture. So let's start with I'll come to this in this figure later on. So let me start with a practical signal, right? Which we can generate in the laboratory. So we can always generate a shorter pulse. We can always generate a shorter pulse in the laboratory. Suppose we have we are generating a shorter pulse, which is something like this, right? It's a shorter pulse with 0 to delta is the width of this pulse, and suppose 1 over delta is the height of this pulse, right? And we denote our signal. Suppose this is delta with sub delta of t, right? Suppose we denote it by this delta function with the sub delta, with a subscript delta. This is the notation for this function. This is a function, time domain function, which has a finite duration. Now it has a finite duration, so we can generate it with some peak value. And if you concentrate on this signal, if you see the area of this signal, it's basically 1 over delta times delta, the height, and the multiplication of the width, which is unity, right? So the area of this signal is unity. Now maintaining the area of this signal, if we compress this signal in such a way that we decrease this delta, we decrease the width of the signal, right? So this signal would be compressed. If we try, if the area is maintained, because the height is 1 over delta, right? You can see the height is 1 over delta. So if we maintain this area, if we decrease the delta, 1 over delta would increase, right? So if we decrease delta, 1 over delta would increase. There would be an increase in 1 over delta. The height would increase. And when this delta approaches 0, it means this height 1 over delta approaches infinity, right? So but the area still, if you observe the area of this function, it is unity. The area of this function is unity, 1 unit. So if we can generate a pulse with a very shorter duration such that its duration approaches 0, right, while maintaining the area of that function is unity, we call it a unit impulse function. And that function is basically represented on time axis, that is represented as an arrow. We cannot increase this height to infinity, right? We don't know how up it should go, but we just put an arrowhead that okay, this is a pulse with duration delta approaching 0, a very shorter pulse, right? And its area is unity. So we just represent it by this arrow. So if I write the same, if I write it mathematically, so basically now your and we say that our delta of t is basically, this is our delta of t. Our delta of t is basically it's the same function, the function which we have a finite duration, right, with delta approaching 0. So it's our impulse, unit impulse function is basically defined this way. There, our unit impulse function is just the shorter pulse with the pulse duration approaching 0, keeping in mind that the area of this pulse is unity, right? So we represent the unit impulse here graphically by this as shown in this figure. We represent it graphically as shown in this figure. Now this is a very important signal. It is just the basic building blocks of many signals. It's just you need a if I usually give an example of the brick, that you when you connect the bricks one with another, you can just make the whole building. And same is the case with this delta of t function, this delta of t, the unit impulse. You have you collect or you sum many delta of t's, many impulse function, and they collectively make some signal. Or in other words, you can say that you can represent your any signal in terms of delta of t, right? So we will see this later on, that how to represent the signal, but for the time being, just to emphasize on its importance, delta of t is now if we define delta of t, it is basically the it is basically this this function. It's basically the limiting idealization of this short pulse. It's basically the idealization of this short pulse, a pulse with a very shorter duration and area with a unit area, right? It is a idealization of this short pulse. Now once you know this, that now you should be familiar with the as you know that the area of this pulse is unity. It means if I integrate delta of t, right, from minus infinity to plus infinity, if I integrate it, it would give me unity, right? So this integral is basically unity because the area is unity, as we have already seen that this area is unity. So if we integrate the unit impulse from minus infinity to plus infinity, it's unity. Now we can also represent the delayed version of the unit impulse. For example, if the unit impulse, some delayed version of unit impulse occurs somewhere here at t naught, right? Unit impulse, so you can represent it as delta of t minus t naught. This is the delayed version of unit impulse which occurs when this is equal to 0. T minus t naught is equal to 0, which means t is equal to t naught. So this unit impulse basically is at t is equal to t naught, right? Now similarly you can have its advanced version. For example, you have delta of t plus t naught, which is an advanced version of the delta function. So this unit impulse, this would be this would occur when t plus t naught is equal to 0, or basically t is equal to minus t naught. So on time axis, this is the time axis. So on time axis, if you want to observe this delta function, delta of t plus t naught, it is basically at minus t naught here, right? So this function is delta of t plus t naught, and this function is delta of t minus t naught. Sorry. I have, this is actually delta, did it a bit incorrect. Let me make this correction. This is delta of t minus t naught, and this is delta of t plus t naught, as we have seen here. Now you can have many other unit impulse. You can have you can represent it as a unit impulse, train of unit impulses, such as this one. For example, this is my time axis, and if I say I have t minus k t naught, right, and I say it's for k suppose 1 to 3. So basically this is delta of t minus, for k equal to 1, 1 t naught plus summation, right? So let me open this summation, delta of t minus 2 t naught and plus delta of t minus 3 t naught. So if you want to plot it on the time axis, basically you have a delta function which occurs at t naught, right? So we have basically a delta function which occurs at t naught. So this one is a delta function at t naught, another delta function at 2 t naught, 2 times t naught, and another delta function which is here, 3 times t naught. So you can represent this the train of impulses. Now if you change this limit, suppose it is from minus 1 up to 3, so you would have minus 1 and 0 as well. So you can add 2 more, which should ideally come for t equal to minus 1. It would be t minus 1 t naught plus delta of t minus 2 times t naught. So this is basically delta t plus t naught, the first one. This one is delta t plus t naught, then delta t plus well, t minus 1, then you should have 0 here, right? 0 here, not minus 2, it should be 0. Delta t minus because here in this summation we have minus 1, then 0, then 1, then 2, and then 3. So you have minus 1, then 0, then 1, then 2, and then 3. So there are 5 terms in this summation. So basically you can draw 2 more impulses at 0 and at minus t naught, right? So these are the train of impulses. So you can change this one and find the train of impulses. Let's see the how this unit impulse function sample the signal, because I told you that we would learn the sampling property, of unit impulse. So how it samples the signal. Suppose you have a signal x of t. Which starts somewhere from minus infinity and goes up to infinity. Suppose this is x of t. And if you multiply this signal with a unit impulse, suppose that unit impulse occurs somewhere here at t naught, right? So t naught is this instant, right? Now if you multiply these two signals, now you can see what would it, suppose I want to find out this product delta of t and this one delta of t multiplied by the x of t multiplied by delta of t minus t naught. I want to find this product. Now you can see graphically, that although x of t exists for the whole time axis, right? It has some values. At every instant the value is changing. But you can see the second function, and this second function has 0 value in this towards the left side of t naught, and it has 0 value towards the right side of this t naught. So if you multiply any signal with a 0 in this time instant, you would get 0. Similarly, after t naught, if you multiply any signal, so for the product in this range and this one, this signal x of t, you are multiplying x of t with delta t minus t naught. So x of t towards the left of t naught has some value, but we are multiplying it with delta t minus t naught, so it has no value, 0 here. So if you multiply this value with this 0, you would get 0, right? So if you try to plot the resultant, below, on the time axis for this product, what would you get? Now from here up to t naught, we have the product which is 0. This signal multiplied by 0 is 0 here. Now at instant t naught, this signal is delta of t minus t naught, right? And the value of this function x of t at t naught, the value of x of t at let me write it here. At t equal to t naught, the value of x of t is basically x of t naught, right? T sub naught. So this particular value would be multiplied with the delta function. So this product basically had some value, it has some value. So what would happen? You would have you can represent it as this product. You can represent here an impulse multiplied by x of t naught. So this is basically delta of t minus t naught multiplied by x of t naught, a single value, x of t naught, right? X of t naught. So you have a single value, x of t naught, delta of t minus t naught. Now after t naught, again if you multiply x of t with a 0, you would get a 0. So here in this range also you would get a 0. So basically you get the sample of x of t after this multiplication. If you multiply the signal x of t with delta of t minus t naught, you basically get an impulse which is scaled by x of t naught, delta of t minus t naught, right? This is basically you are actually sampling x of t at instant t naught wherever this impulse function occurs. So if you want to change, if you want to find the sample of x of t at some other instant, for example 2t naught, right? So you multiply x of t, you can multiply x of t with delta of t minus 2t naught, right? So what would happen? This product will have only value at this instant at t equal to 2t naught, because this function only is available at t equal to 2t naught. In the rest of the time this function is 0. So the product of two functions would be 0 if one of them is 0, right? So this is only present at this particular instant. Now if you want to integrate this signal, suppose you want to integrate, you want to multiply x of t with delta of t minus t naught, and you want to integrate it from minus infinity to plus infinity. What do you get? Now as we know that this product has a value only, we can rewrite this integral from minus infinity to plus infinity. This is x of this product will have value only at t equal to t naught. So this product basically will have only this product is same as this product, right? So now this particular value x of t naught, it's just a single value of that function. It's a kind of single value which occurs at t naught, right? So that would be some numeric value, maybe 1, maybe 2, maybe 1.1, maybe 0.5, whatever it is. You can put it outside the integral. It's a kind of constant now for you, and you can rewrite this as delta of t minus t naught dt, right? But we know that this integral, as I said earlier, that this integral is equal to unity, because you are integrating an impulse which occurs at t naught, and the area, the integral which gives you the area of the impulse is unity. So basically you are left with x of t naught. So this is the sample of that, the sample of x of t at instant t naught. So this is the sample, this is the sample of x of t at t equal to t naught. This is how you take the sample. You can sample the signal, you can have multiple samples of the signal. This concept is very useful in integration as well as the sampling of the signals. So basically you get the sample of the signals. Now in the next lecture we would see how is it this unit impulse is re it is related with the unit step function.